Welcome back to the deep dive. Today, we're jumping into something pretty crucial if you're working with cloud-native apps. We're talking about managing secrets in Kubernetes.
Yeah,
The sensitive stuff like database credentials, API keys,
right.
all that. And we're going to focus specifically on a really powerful tool that's, well, changing the game. The External Secrets Operator, or ESO. Now, if you've been around Kubernetes, you probably know that handling secrets, especially dynamic ones like the kind you get on demand from HashiCorp Vault, it can get tricky. The older ways often involve this thing called a sidecar. And, well, as we'll find out, sidecars bring their own headaches, particularly around resource usage. So our mission for this deep dive, we're going to unpack exactly how ESO gives us a much cleaner, more elegant way to do this. It really shifts how dynamic secrets work in Kubernetes, potentially saving resources, sure, but also just simplifying how you operate. It's a big deal. We think this knowledge can be a real shortcut for you to get up to speed on modern Kubernetes security. Okay, so let's unpack this. We often hear about sidecars for secret management, especially with Vault. For anyone maybe less familiar with that specific detail, what is a sidecar here and why is it the problem ESO tries to fix? What's the big architectural shift ESO brings?
Yeah, that's a great place to start because understanding the before really highlights why ESO is so useful. So the traditional HashiCorp way often is to inject what's called a Vault agent sidecar. Think of it like a small helper container that runs right alongside your main application inside the very same Kubernetes pod. Its whole job is basically to talk to Vault, grab the secrets, and then somehow make them available to your application.
Okay, like a little dedicated messenger for secrets in each pod.
Exactly. And, it works.
Yeah.
But the problem is the overhead. Each one of these sidecars needs its own memory, often like 50 to 100 megabytes, and its own CPU cycles.
Just for the sidecar.
Just for the sidecar, yeah. I actually worked on a project where this just killed our dev environments. Felt like paying for 2 apps for every one service. Now imagine you've got hundreds, maybe thousands of pods in a big cluster. Each needs secrets, each gets a sidecar.
Right, that adds up fast. You're talking significant resource waste.
Precisely. It becomes a real scalability issue
Yeah.
and just eats up cluster resources unnecessarily.
Mhm.
And this is where ESO changes the whole picture. It's a fundamental architectural shift. Instead of a sidecar in every pod, ESO runs as a centralized Kubernetes controller. Just one deployment, typically, in your cluster.
Okay.
And this controller is responsible for talking to the external system, like Vault, fetching the secrets, and then synchronizing them directly into native Kubernetes secret objects.
So no sidecars needed in the application pods at all.
Exactly. It completely eliminates that need. Your apps get the same access to the secrets, but without all that complexity and resource drain at the pod level, it's much cleaner, much more efficient.
Yeah, the resource savings alone sound pretty compelling. But here's where it gets really interesting, Winnie. What about dynamic secrets? The ones that aren't just static values but are generated on the fly, maybe with short lifetimes. How does ESO handle those with something like Vault?
Right. That's absolutely critical because dynamic secrets are a huge part of Vault's power. And ESO is built specifically to handle them really well. It uses this pattern, this specific generator called Vault Dynamic Secret.
Okay.
Think of this Vault Dynamic Secret as ESO's instruction manual for getting dynamic secrets from Vault. See, unlike just fetching a static key-value secret, dynamic secrets often need Vault to generate credentials. This usually involves ESO sending a specific request, like a POST request, to a particular Vault path.
Got it. So it's not just reading, it's asking Vault to create something new.
Exactly. So let's say your app needs database credentials. You define a Vault Dynamic Secret object in Kubernetes. In that definition, you tell ESO, okay, go to this Vault path, say database grid is my AppRole.
Yeah.
Use a post request to generate credentials. You can even specify parameters like a TTL, a time to live, maybe 1 hour for 1 hour.
So the credentials are only valid for an hour.
Right.
Yeah.
Short-lived.
Yeah.
The config also tells ESO which Vault server to talk to, and importantly, how ESO itself should authenticate to Vault, usually using a specific Kubernetes authentication role we can talk about later. Then, whenever ESO needs to refresh this secret, it follows those instructions, goes to Vault, gets brand new unique credentials, ensuring your app always has fresh temporary access.
Okay, so that Vault Dynamic Secret is the blueprint for asking Vault. But then how do those fresh credentials actually get to the application? How do they become like normal Kubernetes secrets that my app can just use without knowing about Vault or ESO?
Right, that's the next piece, and it's handled by the external secret resource. This is kind of the orchestrator. Once the Vault Dynamic Secret Generator has done its job and fetched the fresh data from Vault,
Yep.
the external secret resource takes that data and uses it to create or update a standard native Kubernetes secret object. So, following our example, if the Vault Dynamic Secret got database credentials, the external secret would create a regular Kubernetes secret, maybe called MyAppDB creds, right in your application's namespace.
Oh, okay. So the application just sees a normal Kubernetes SQL.
Exactly. That's the beauty of it. Your application consumes this secret, the standard Kubernetes way, mount it as a volume, use it for environment variables, whatever. The app code doesn't need any special Vault libraries. It doesn't even know ESO exists. It's completely decoupled.
That's huge for keeping applications simple.
Totally. And the external secret definition itself also have a key property, refresh interval. You might set this to, say, 30 meter. This tells ESO, hey, every 30 minutes, go back to Vault, use that Vault Dynamic Secret blueprint to get fresh credentials, and update the Kubernetes secret. It makes rotation seamless and automatic for the app.
Okay, that seamless handoff to native Kubernetes secrets is a really big advantage. But, all right, this raises a security question for me. If we're getting rid of the sidecar in each pod, how does ESO itself securely talk to Vault? How does it handle authentication and make sure only the right things can access secrets? It feels like a lot of power in one place.
That's a critical point. Security is obviously paramount, and ES has a really solid model here. It leverages Kubernetes native authentication. So instead of juggling separate Vault tokens or some initial bootstrap secret for ESO, it uses something called service account token projection.
Okay, what does that mean exactly?
It means ESO, the controller itself, running in Kubernetes, authenticates to Vault using its own Kubernetes service account token. Vault has an authentication method specifically for Kubernetes. It takes that token from ESO and validates it directly against your cluster's Kubernetes API server.
Ah, so Kubernetes itself verifies ESO's identity to Vault.
Precisely. It provides really strong identity verification. And a huge benefit here is what's often called secret zero elimination. You don't need some pre-existing secret to get ESO started talking to Vault. The service account token is the initial trust anchor provided by Kubernetes itself.
Okay, that simplifies bootstrapping quite a bit.
It does. And beyond that initial auth, ESO relies on a defense-in-depth approach using dual authorization.
Dual authorization.
Yeah. First, you've got standard Kubernetes RBAC role-based access control. This controls who in your cluster is allowed to create, read, or modify those external secret resources we talked about.
Right, standard K8's permissions.
And second, you have Vault policies. These policies are specifically bound to the Kubernetes authentication role that ESO uses when it talks to Vault. So both systems have to say yes. Kubernetes RBAC must allow creating the external secret, and the Vault policy associated with ESO's role must allow accessing the specific secret path in Vault.
I see. So even if someone could create the external secret object, if the Vault policy doesn't allow it, they still can't get the secret data?
Exactly. It provides a really strong security boundary. You need clearance in both Kubernetes and Vault.
That dual layer sounds robust. Is it tricky to manage in practice? Two sets of policies. And thinking more broadly operationally, how does ESO handle the whole life cycle? Creation, rotation, cleanup, and what about resilience? If ESO goes down, do all my apps lose secrets?
Good questions. On managing policies, yeah, it's two layers, but it often aligns well with team responsibilities. Platform or cluster admins might handle the Kubernetes RBAC side, who can request secrets via external secret objects. And security teams or Vault admins handle the Vault policies, what secrets can actually be fetched. It enforces that separation of concerns. Operationally, ESO is designed for this stuff. Lifecycle management is fully automated. Creation happens when you deploy the external secret. Rotation, handled automatically based on that refresh interval we mentioned, keeps secrets fresh, usually every 15 to 60 minutes for dynamic ones.
And cleanup, that's important.
Crucial.
Yeah.
If you delete the external secret resource, ESO will automatically clean up the corresponding Kubernetes secret it created, especially if you use the creation policy, owner setting. No stale credentials left behind.
Nice. What about HA and resilience then?
Right. The operator itself uses what we call eventual consistency patterns. It has built-in retry logic with exponential backoff. So let's say Vault is down for a minute or there's a network hiccup. ESO won't just give up. It'll keep serving the last known good secret from the Kubernetes secret object to your applications, while it intelligently keeps trying to reconnect to Vault with increasing delays. You can configure things like max retries and the backoff strategy.
So apps keep running even if Vault has a short blip?
Exactly. It ensures application continuity during transient issues. And for multi-tenancy, ESO is really flexible. You can use SecretStore objects, which are namespace specific, great for isolating teams or apps.
Okay.
Or if you need to share access configuration across the whole cluster, You can use ClusterSecretStore. These are cluster-wide. But you still use RBAC to control which namespaces or service accounts can actually use that shared store to fetch secrets. It allows for pretty granular control in shared environments.
Okay, that covers a lot of the operational robustness. So if an organization is thinking, all right, this sounds good, we want to put this in production, what's the recommended way to deploy it, and how do we keep an eye on it? What about observability?
Yeah, for production, you absolutely want high availability for the ESO controller itself.
Yeah.
That usually means deploying multiple replicas, say 3, and enabling leader election.
Leader election.
Yeah, it's a standard pattern.
Right.
Only one replica is active at a time, the leader, doing the work. If that one fails, another replica automatically takes over. The easiest way is often using the official Helm chart. You'd run a command like helm install and set flags like the replicount 3 and leader elect true. This gives you that resilience for the controller itself.
Got it. Makes sense. And monitoring.
ESOS is pretty good here too. It exposes metrics in the Prometheus format, which is kind of the standard in the Kubernetes world.
Yeah.
So you can easily scrape these metrics and monitor things like how many secret syncs are happening? Are there any errors syncing secrets? How long are the sync operations taking?
What are some key metrics to watch?
You definitely want to watch external secrets. STOTL just tracks activity. Then external secret sinkles SOS are super important for spotting problems. And maybe external secret reconcile duration seconds to see if syncs are getting slow. Good monitoring here gives you confidence that your secret pipeline is healthy.
Okay. And disaster recovery, like cross-region stuff.
Yeah, that's more about your Vault setup, but ESO can work with it. If you have Vault replicated across regions, you can configure cluster secret stores in EHAS to potentially fail over between those Vault clusters. And just generally, the controller architecture itself makes ESO more resilient during things like cluster upgrades or node failures compared to the sidecar model. If a node with a bunch of sidecars goes down, that's a lot of apps potentially impacted. With ESO, if a controller replica node fails, another replica just takes over leadership.
Okay, that makes sense. Let's try and connect this to the bigger picture then. How does ESO really stack up against, say, the Vault sidecar injector we talked about, or maybe the Vault CSI provider? If you're evaluating options, what makes ESO stand out for production?
Yeah, that's the key comparison. Let's break it down across a few important dimensions. First, resource overhead. We touched on this ESO. Minimal, just the central controller. Vault sidecar injector. High, 1 sidecar per pod. Vault CSI provider. Medium, typically a daemon set running on each node. ES is a clear winner here.
Right.
Big difference. Second, dynamic secrets. ES handles them great. Vault sidecar injector also handles them well. The CSI provider. Its support for true generation of dynamic secrets is a bit more limited. It's often better suited for mounting existing secrets.
Okay.
Third, and this is a big one, native Kubernetes secrets. Does it create standard K8s secret objects? ESO. Yes. This is huge for compatibility. Sidecar injector, no. CSI provider, no. They inject secrets directly as files or vars, bypassing the standard K8 secret API.
So applications need to know how the secret is being provided if they use those other methods?
Pretty much, yeah. Which leads to the fourth point, application changes. With ESO, usually none are needed. Apps just consume the standard K8 secret. With a sidecar or CSI provider, apps often need specific logic to read from a certain file path or environment variable injected by those tools. It can mean modifying your app code.
Less ideal.
Often, yeah. And finally, secret rotation. All three handle automatic rotation, which is good. But ESO does it by updating the native Kubernetes secret, keeping that standard interface consistent. The others rotate the files or NDVARs they manage directly.
So weighing all that.
Well, if you value minimal resource overhead, seamless integration with native Kubernetes secrets, and avoiding application code changes, ESO really does look like a very strong, often the preferred option for production environments, needing robust Vault integration.
That's a really clear comparison. It definitely highlights ESO's strengths. Now, what's fascinating here is, can we push ESO even further? Are there more advanced things you can do with it, showing off its flexibility, beyond just syncing one secret type?
Oh, absolutely. ESO is quite flexible. One cool advanced pattern is multi-source or multi-engine secret composition.
Meaning
You can define a single external secret object that pulls data from multiple places, maybe multiple paths within Vault, even different Vault engines, or potentially other external secret managers if configured. For instance, you could grab a database connection string from Vault's database engine and, in the same external secret, grab a TLS certificate from Vault's PKI engine. Both pieces of data end up in the same resulting Kubernetes secret.
Ah, okay, so grouping related secrets together, even if they come from different vault mechanisms.
Exactly. It simplifies things for the application that needs both pieces. Another really powerful feature is template-based secret transformation. ESO supports using Go templates within the external secret definition.
Like formatting the secret data.
Precisely. But you can do complex stuff. You can take the raw data fetched from the external source and completely reformat it before it gets put into the Kubernetes secret. A classic example is creating native Kubernetes TLS secrets for things like ingress controllers. You might fetch the certificate and the private key as separate fields from Vault's PKI engine.
Right, like certificate and private key.
Yeah. And then use a Go template within your external secret to structure that data into the specific format Kubernetes expects for a kubernetes.ils top secret, with the data keys named tls.crt and tls.key.
Oh, wow. So ESO can directly create ready-to-use TLS secrets for ingress from Vault PKI outputs.
Exactly. It completely automates that common workflow of issuing and managing TLS certs for your services. These kinds of advanced features really show how powerful and integrated ES can be.
So what does this all mean for you listening? Well, we've dug pretty deep into the external secrets operator. Hopefully you can see how it really simplifies what can be a very tricky problem, managing secrets securely and efficiently in Kubernetes. It boosts security with the robust native authentication and, crucially, saves resources by getting rid of those sidecars. Ultimately, it offers a more efficient, more secure, and frankly more resilient way to handle sensitive data right within your Kubernetes environments. And maybe a final thought to chew on. Thinking beyond just secrets, how might adopting a controller-based approach like ESO for managing external resources influence your broader cloud security architecture? Could it inspire similar patterns for other types of configuration or policy automation in your workflows?
That's all for this topic. Stay tuned for the next deep dive.